So putting all aside, unless there's other questions about it, other concerns, right? So just be aware, look at your email, right? Check Canvas. I will, right? If it does come down to that we're going online, I will immediately send out a notification on Canvas. All right? So as soon as I know. All right. But I'm finding out through email as well. All right.
I just want to help everybody.
You know what? What's that?
I've been to Costco for a whole week and tried to get toilet paper. And there's none.
Yeah, well.
You gotta go there first thing in the morning.
Yeah. People are panicking, right?
Yeah.
It's nothing to panic about. It's gonna hopefully come and go, but we gotta deal with it, and hopefully it doesn't hit us as hard as it did with China. So, yeah. Yeah, it was sent out yesterday, I believe, and it wasn't good, and she fixed it. So if you took it yesterday, there's a little survey asking you about computers, I think, and it wasn't that good, and she fixed it. She sent an email out this morning. So maybe you might want to take it again if you already took it. I think through your student email, whatever that might be.
Is it optional?
It's optional, but it's information too. Even if you do have the internet and a computer at home, good internet, it's helpful for them to know that, right? So they can plan out how many computers and how many hotspots they need in general for people. Okay, because that is the hard part, right? We don't know, right? So we're worried about our students that don't have internet access and computers at home for this possible transition, right? Again, this is a possibility, right? It is not a guaranteed thing. So let's assume that we're going to be here Monday and we're taking the test on Wednesday. All right? That's the good assumption, right? If something happens, yes, it'll be postponed for a little bit. All right? All right.
Either way, you're going to have us prepared.
Yes. Either way, we're going to do this, and we're going to talk about probability, whether you want to or not. All right. Those are pros.
There's some probability in that as well. The probability of us being here is.
All right. So I wanted to move on. So last time we talked about 3.4. We didn't fully finish it, but I want you to look through that section and make sure the notes are understandable. If it's not, let's come back with questions on Monday on 3.4. But I wanted to move on. I talked about last time how I realized essentially that this book was missing stuff. This book is missing information that we needed, that we are required to cover. And so this is the Andre special section. I'm calling it 3.7. There's no 3.7 in the book. So here's the Andre special, okay? It's like a good stew.
Sweet.
All right. So that's why it looks different, right? And it is different. I actually did borrow this from Mary Martin, her notes, and I kind of just whittled down her notes to be able to essentially make this up. Mary Martin's a really excellent stats teacher at CRC. That when I first got stats, she gave me all her stuff, and I highly trust her. All right. So let's talk about it. So we have talked about these two ideas before, without replacement and with replacement. Without replacement, what we are really thinking of is that without replacement means that we have a dependent. Whoops. Do I have a place for this? Yeah, I do. Look at that. Backing up. Oh, wait. We are recording, yeah.
That's all right. Totally fine.
All right. So without replacement means that we say the trials are dependent. With replacement, we say that the trials are independent. Independent is the good case. Independent takes less thinking about it, essentially, right? Essentially, what we're going to do is when we talk about and statements, so we talked about last time, we talked about and statements mean something mathematically. If I say and, we should be thinking of what operation mathematically? It's multiplication. Multiplication, there's a multiplication rule, and the or is addition rule. Yeah. So, and they're not just straight up, right? You add them, or you multiply them. unless we know we have independent events. If we have independent events, then we are.
Is it or and?
Oops.
Just kidding.
I might be a little tired. Checking to make sure you're all awake.
Yep.
Because at least one of us is. So and equals multiplication and or equals addition. So with independence, when we have independence, then it is straight up multiplication. So if I had like 3 reds kind of thing. Oh, I just noticed this is an example. I didn't notice that last night. So if I have all 3 reds are, all 3 candies are red, then I literally just multiply the probability of getting a red times the probability of getting a red times the probability of getting a red. What is the probability of getting a red if I have 13 red candies and 7 yellow candies in a candy dish? 13 out of 20. And we are going to multiply those, each one, because I'm putting the candy back in. It's like I pick it and then I put it back in. You know, I'm just getting my coronavirus all over it and then putting it back in for somebody else to eat. So we shouldn't be making jokes about that right now.
No, that's fine.
I actually like it.
Most of this class is Gen Z. I promise you they
I really like it.
All right, so and we would do something with that, but I'm just going to leave it there, and we'll talk about actually multiplying those in a second. So that's how the probability would go for independent stuff. But if I say the same thing for dependent system, it changes things. And we talked about that formula before when we talk about dependent, and this is in general, the multiplication rule in general is this. So if I had 3 things, where you have A and B and C, I think I mentioned this before when we were doing the card thing. Right, we talked about some cards. We were playing a royal flush, trying to get a royal flush, and that was a dependent system. This is the probability of getting A times the probability of getting B given A already occurred times the probability of getting C given that A and B already occurred. A and B already happened. So it is a given condition, right? So it whittles it down. It looks horrible, this notation, but it's really not that bad to calculate these things. All right, well, we'll see how it's not bad. All right, so but if we always assume that a system's dependent, then it usually works out. In some cases, we won't be able to use the dependent idea because maybe we only have a percentage. I don't have essentially how many things out of a total kind of scenario. I don't have a fraction that I can manipulate and work. And think about like what happens if I eat that candy. Right?
You get coronavirus.
So if I want all 3 are red and we are without replacement, we are in a dependent system, right? I am literally eating it, and no, I'm not getting coronavirus, hopefully. So if I'm eating them, then they go away. So if I get the first one, there we go. I don't know what that noise was. It just came out of me. So the probability of getting a red times the probability of getting the second one to be a red, second red, given the first was red.
Okay, what?
Do you understand the notation here?
No.
So, yeah, so here the second one, so here's the first red. So I'm just trying to explain notation, right? But if we'll see the numbers a little bit easier. So probability of pulling the first red. So how many reds do I have? 13. So this would be 13 out of 20. And then I'm calculating the probability that the second candy, I randomly choose and mix my hands in the bowl kind of thing, right? And pull out that red candy. What's the probability that I get the red when I already ate the first red candy?
Okay, so
13 out of 19.
sorry, 12
I already ate one, so how many red candies are in the bowl? 12 now? 12 out of 19. We only have 19 candies left in the bowl. Right. Because I ate it. It's gone. Right. But I also had a third candy because I'm hungry. Right. I am kind of hungry today. So, all right, third red. I want a third red because really all I like is red. So, but it's given that we already had 8. The first one was red, and the second one was red. I already ate those things. I ate 2 that were red. So I'm trying to show the notation here. All right, that's all I'm doing here. If we're not sure what I mean, hopefully we understand this dependent system. I only had 12 out of 19. I ate that other red one, that second red one. So how many reds do I have now?
11.
11 out of 18.
Nice. 11 out of 18. And there's my multiplication. A little bit different than the bottom one, right? So these are a little bit different numbers, kind of thing. But dependency matters, right? So we're talking about it. So dependent system versus independent system. Independent makes it a little bit easier, right? When we have independence.
Well, how is the first grade 13 and 11? Can it be the third grade? That's my thinking.
That's it. Well, it's the candy bowl, right? So you have candy bowls, you have 13 red candies in there right now.
But you saying the
So
first
I have
one.
13 out of 20. I eat one. I only have 12 left out of 19.
Right.
I eat another one, red one. I have 11 out of 18.
But wouldn't that be the third one? No.
Yeah, that's the third candy right here. I ate that one now. So all 3 are gone.
But you got to mark this first grade.
Yes. So there's the first red. Second red. Third red. Right? Numerator's going down as the denominator's going down.
But I don't see you listed it as the third grade. You listed it as the first grade.
Oh, sorry.
That's what's.
I'm off. I apologize. I see what you're saying. This is where Nas's idea of using color would help.
It's okay, because
Right.
I'm using color right now. I am. Now the different coloring them.
This goes here. This one goes with that probability. Yeah, was it Joel?
Yeah.
Joel.
Okay, cool, yeah, I like it. Looks good.
Right. So I only have 3 probabilities that I'm calculating there. Then I'm multiplying them together to find out what that is. I'm not going to do that at this stage, but we'll do it on the next real problem. Somewhat real problem, I should say.
So the whole fraction, the 12 over 19 is under that chunk that says the given chunk, like blah blah blah,
So
given
that's-
blah blah blah.
That
I'm
should
just
be
making
it,
sure I
right?
understand it.
Yeah, this should be a different color, right? Here's blue.
Gotcha.
These should be like red or something, and
Gotcha,
this should be
yeah.
green. If I was a good teacher, I would do that.
Oh my god, you're terrible.
I didn't use colors.
We love you.
All right. So when applying the multiplication rule, always consider the events are independent or dependent and adjust the calculations accordingly. So we have to kind of ask this question whether it's independent or dependent as we go. So for example 2 here. So let me move it up.
I do
Oh,
have a question
yeah.
regarding to the with the person, the dependent. So after you got all those numbers, do you have to conclude it? Like give it a conclusion or like what's the total?
Yeah, we should actually figure out what that is.
Okay.
So probably in decimal form, in this case, is the easiest. GeoGebra, I will actually show GeoGebra here, and GeoGebra can do fractions really nicely too.
Okay.
So I'll show GeoGebra in a second. This is just the initial problem, so I'm not going to do it right now. But
Okay.
Does
So-
it say and in between first red and second red, or what's that little thing?
yes, and.
Okay. Cool.
So both of those things happened.
Cool. Yeah.
So,
I
and.
got you.
All right, so let's continue, and I will do it here. We'll calculate the probability here, and typically we want decimals. But we could use percentage. We could use fractions, but sometimes the fraction gets so just ginormous that we don't want to deal with it. All right. So again, it is a choice. All right. So what is the probability of getting 5 heads in a row? So let's talk about this. I'm flipping a fair coin, right? I don't have a coin in front of me for some reason. I'm flipping a fair coin 5 times. Right? Fair just means that, right, you have a 50-50 shot of getting heads or tails. Right? It's not weighted on one side or something like that. I'm flipping this coin, right? I got a 50% chance of getting heads or tails, kind of thing. And I'm flipping it 5 times. But getting heads 5 in a row is a lot more difficult, right, than getting just one head. You get that?
Yes.
So this is an and statement because I'm getting the first time I flip it, I want a head. Right? And the second time I get it, I want a head. And the third time, I want a head. You get the and statement? It's not an or statement. I don't want the first one to be heads or the second one to be heads because that would mean I could get a tail on one of those and it would fit the category. In effect. So these are and statements. So we want, right? What we're talking about is the probability. So I am just really trying to go over this notation and us understanding that we can rewrite it with the notation so we can understand what formulas to apply. So this is the probability of getting a head, and it looks like hand and hand and hand, but that's a head and a head and a hand and a head, right? Okay. So we get, so which would be a multiplication rule, right? Is this an independent thing or is this a dependent thing?
And it can.
You're not taking it away, so it's independent. I mean, nothing's being taken away.
If I flip one coin, right, I
Just
get a
going
head.
back in there, yeah.
Does me knowing I got a head on that first one change the probability of getting a head on the second?
No.
No. That is an independent event. Like as we know what independent means, it has nothing to do with that first one. Right, probability wise. Doesn't change the outcome of that second thing being a head. So these are independent, which means it's nicer. I get probability of getting a head times the probability of getting a head for the second one times the probability of getting a head for the third one times the probability of getting a head. Do I really have to write all this down? There must be an easier way to write this. Yeah.
Probability of H.
Fifth power. Look at that. I used some colors.
Woohoo!
Beautiful. Right? Much easier to write that. I don't want to write it the other way. So let's write it that way. What is the probability of getting a head?
Oh boy.
I think I heard somebody whisper it. It's the voices are back. One of the two. Yeah, 50%. Let's write it as a fraction. So what's that? 1/2. We're talking about 1/2 raised to the fifth power, which I think would be 1/32. So we can write it as the fraction again, as long as I do this multiplication. Right? I mean, if you give me that on the test, you got most of the points. Right? If you don't, right, do that little step of actually multiplying them. Because you know what it is, and that's the main objective. So. Questions on that? All right. Yeah. 1/32. Sorry, I did. 1/2. So right, 1 out of 2 shots for a head. You got right head or tails. The outcomes. I'm looking for a head. I only have one event, one thing in the event, but I have 2 things in the sample space. All right. So let's talk about the next one. So kind of a real world problem. So we have red and green color blindness is the most common form of color blindness and affects 6% of males. So I think it's different, from my understanding, it's different for females too. I've heard this before. So it affects 6% of males. If 4 unrelated males are selected at random, what is the probability that all 4 have red, green color blindness? So I'm looking for that probability of getting that first male to be colorblind, and the second male, and the third male, and the fourth.